I've run this for several years, and you'll notice on the second page, I've got a couple of rows just X'd out. The reason for that is those two never work. And in fact, I probably should have X'd out the second one. I think we'll just focus on the first one, where you have 5 mils of 0.1 molar silver nitrate and 5 mils of 1 molar ammonia in 100 milliliters of solution. So we'll just not do the second part. Okay, so that's what you do first. You form that solution of known concentrations of silver nitrate and ammonia. That's your starting point. So we've got a solution here in our 100 milliliter flask of 5 milliliters of 0.1 molar silver nitrate.
No questions, their answers, just lab board.
Yeah, right. There are no special questions in this one.
No pre-lab or anything?
No pre-lab and no post-lab questions. And then we put in 5 milliliters of 1 molar ammonia. Now, the ammonia is dissolved in water, and if you open the cap, you're going to smell ammonia. But let's see. I did a calculation on the back side just to prove that most of the 1 molar ammonia is in that form. 99.6% is in ammonia form. Because sometimes you'll see when ammonia is in solution, sometimes you'll see it listed this way. Ammonium hydroxide. That's a very small part, like 0.4% of all the ammonia in that solution is in this form. Most of it is like that. So we're going to treat it as if it's all that much. Okay, so that's our starting point. Then what we want to do is, let's see. Okay, that's the dilution part. Those two go in here and dilute to 100 mils with water. Then you transfer all of that solution to an Erlenmeyer flask. So you're going to put all of this into an Erlenmeyer. This is a volumetric, this is an Erlenmeyer. So it all goes in there. Then we're going to titrate it with standard, I should have drawn it down. So this goes in here, and now we're going to titrate it from a burette. Right? We're going to titrate it with standard 0.1 molar KCl. So what you're doing is you've converted. This is all in solution, silver nitrate. So everything you put in here is now the ammonia complex ion. Okay. Now we're going to add chloride ion, and it's going to compete with this complex ion for the silver. And the reactions are given on the, actually the first page. So as it competes for the silver ion, it will eventually, the concentration of chloride and silver in solution will eventually exceed the solubility product and form a precipitate. That's our endpoint. So when we get to the endpoint here, we're shining a light. Remember, shining a light. Right. And we're looking at it from here. And looking for the light beam. When you can see the light beam, then you have produced silver chloride in solution. That's your endpoint. And the reason we use this method is because it's more sensitive. The original method, huh?
So it shows up better that way.
Yes, right. If you use just your normal vision in room light, you'll overshoot the endpoint every time. But this will get you right on the endpoint. Okay, so, and we'll probably put a magnetic stir bar in the bottom. So we won't have to swirl it around. So that's the mechanics of the experiment. You're going to get a volume here. Right. So you got these concentrations to start with. You added this volume. Now what do you do with it? That's the tricky part. What we've got is, let's see, I'll leave that there. What we've got here is the equilibrium expression. The equilibrium we established here is silver ions plus 2 ammonias yield. I'm trying to remember the proper naming for that, nomenclature for complex ions. I think it's diamino silver 1+ is the way you name that. I got a document there. Can I bring it with me? No, I didn't. It must be in my new river. I got formation constants. Yeah, I got a bunch of formation constants. Okay, never mind. And the KF for this, that's what we're after. We're after that value right there. The KF for this then would be the concentration of the ammonia complex ion, silver and ammonia squared. But that's not going to get us where we want to go, right? Because we don't know. We know this one to begin with. We know this one to begin with. We don't know what this one is. So we need to couple it with our titration. Yeah, our coupled reaction is this one yields this one plus this one. And the K for this one, which is solubility product, is equal to simply this. Okay, we know what that value is. Now, Sal Khan used a value of 1.6, I think, times 10 to the minus 10. The one I've got in this method is 1.7. At the top of the second page is 1.7 times 10 to the minus 10 is equal to this. Okay. But what we want to do is both of these reactions are going on at the same time. And as we add chloride in the form of sodium chloride, we are impacting both reactions. Right? So we can combine these two together. And when we do that, we get, we're going to take this one we're going to solve this one for the silver ion. Yeah, solve this one for silver. That's KSP divided by chloride. And then we substitute this right here in that position. And that gives us, I think I will have to erase this. That gives us KF equals the complex ion. Oops. Okay. Divided by, we have the ammonia squared, and then we have the substitute for silver, which is KSP for the silver chloride, divided by the chloride concentration. Okay. All right. Okay. So we know what this is. We know what this is going to be because we're titrating with sodium chloride. At the end point, that's what this value will be, however much was added. We just need to figure out what the equilibrium amounts of these two are. So in order to do that, we could use this expression, except this expression doesn't have the chlorides in it, right? But we can put the chlorides in here, like that, and like that, right? This is before chloride, this is after chloride. So if we lay them out that way, then we have this one, we have this one, we have this one before, and then we have the complex ion. And then we have the after. Okay. Now we can set up our ICE table, because we have to find out what these equilibrium concentrations are before we can do the calculation. Okay, so I find it's easier to do this part as absolute amounts first, and then calculate the concentrations afterwards. Normally we'd have concentration, and then do like that. But it's easier to say, initially, silver is, I erased it already. Silver is, here it is. Initially, silver is 5 milliliters times 0.1 molar. That's equal to 0.5 millimoles. Okay, so we're starting off with 0.5 millimoles of silver. We're also starting off with 5 millimoles of ammonia. Do it the same way. 5 times 1 is this one. We're also starting off with, let's see, oh, okay. I'm assuming for the purposes of this calculation that I left out the potassium chloride. We're using potassium chloride. We're assuming for argument's sake that in order to reach this endpoint, we had 1 milliliter, 1 milliliter. I had it here a second ago. Yeah, 1 milliliter of 0.1 molar potassium chloride. So that 1 times 0.1 is 0.1 millimoles of chloride. So that's before the reaction occurs, we have added 0.1 millimoles. Here we go. Okay, and we had none of this, and we have none of that. So after the reaction occurs, and this is actually combining both before we put any chloride in and after we put chloride in, but it hadn't reacted yet. So that's why we can say this hasn't formed yet, and that hasn't been used up yet. Okay. So when we do that, the end point says that we have used up all of our silver to make silver chloride. Right. So all of this is gone. That means, what's the ratio? Well, it's 2 to 1. So that means we've subtracted 1 millimole of ammonia. Okay. And we've also used up all of our chloride on this side, and it shows up over here. 0.1. Okay. Now, how much is this produced? Well, it's the same as that. It's 1 to 1. Okay, that's the change. Right. Subtract it here, it shows up there. Now, what do we have left? Well, we have no silver left. We have 4 millimoles of ammonia left. We have no chloride from before, but now we have 0.1 millimoles of chloride after, and we have 0.5 millimoles.
So that wouldn't be 1.500, because you got rid of the ammonia over there to put this over.
Where?
The NH3 is with the silver on the right, so you don't add it together.
Well, this is before, and we're producing this much. We're subtracting it over here and adding it over here.
Yeah, but it's combining with the ammonia, is what I'm saying.
Well, we subtracted the ammonia out here. Yeah, yeah, right. They're combined.
Okay, for some reason I thought that would appear over there too.
Mm-hmm. No, there are ratios, right? For every one of these, they're half of these, because they're 2 to 1. Now we have equilibrium values for absolute amounts. Next, we have to calculate concentrations in order to plug them into this equation. So what you need is, what's the volume? What's the total volume now that we've added a titrant to it? Well, we added here 1 milliliter to 100 milliliters. So the volume is 101 milliliters for all of them. Remember, millimoles divided by milliliters is molar. Okay, so that gives you your concentration of, where is it? Here. That gives you your concentration of ammonia here, and complex ion here, and chloride ion here. And this is given 1.7 times 10 to the minus 10, and you can solve for Kf. I know that's a lot of gyrations to get where we're going. But that's where we're headed. And then we compare the KF with the accepted value, which is, did I report the KF? I do a sample calculation. Here's the KF. 10 to the 7th, something 10 to the 7th. I don't see it. It's on the first page. I don't see it anywhere.
KF equals 1.84 times 10 to the 7th.
I think that's calculated, isn't it? Substituting in the combined equation, we have KF equals that, KF equals, which would be one of the experimental determinations. Yeah, that's an experimental value. Here it is. Accepted value, 1.6 times 10 to the 7th. So write that down. 1.6 times 10 to the 7th is the accepted KF.